Between the 8th and 14th centuries, there was a golden age of science, when scholars from the Islamic world introduced a rigorous experimental approach that laid the foundations of the modern scientific method. They transformed the superstition of alchemy into the science of chemistry. The chemical industry has, of course, reshaped the modern world, giving us new fuels, drugs, and new materials. But the methodology and principles of chemistry go back over 1,000 years. I'm Jamal Khalili, and I've been researching the contributions of the scientists of the Golden Age. I'll be tracing back the roots of modern chemistry to these scholars of the early Islamic world. This is Doha, the capital of Qatar. 2 decades ago, none of this existed. All this development has only been possible because of a huge investment of revenue from oil and gas. In other words, the chemical industry. Oil is responsible for much that we take for granted in daily life. From fuels to plastics to medicines, even the tarmac road I'm driving on. The chemical plant over there is processing the gas and crude oil that exists in such abundance in the Middle East. Oil in its raw state is a mixture of many different chemicals, and these are separated out through a process called fractional distillation. The crude oil is heated until it becomes a vapor. The vapor rises up the distillation tower and separates into its different components as it cools. The fractionating tower in a modern oil refinery is a high-tech version of a piece of apparatus called an alembic, used by the Golden Age scientists as a distillation tool over 1,000 years ago. One early pioneer of distillation was the 9th century physician and chemist Al-Razi. Amongst his many writings are the earliest known accounts of using distillation to produce substances like kerosene, sulfuric acid, and pure alcohol. This wasn't for drinking, but for use as a medical disinfectant. Here in Istanbul, Dr. Peter Starr studies the work of the scholars of the Golden Age. He's brought with him an alembic, or still, to show me how the early chemists used it for distillation.
This one is made of copper.
There would have been others made of glass
for
as well.
For example, glass, yes, yes. The important thing about a still is that there's a hot end and that there's a cold end. So the hot end is where the steam is produced. It then condenses and is received into the receiver here. What we would need would be water. First of all, usually distilled water. You could use rainwater.
This will do then?
That will do. And then we'll need whatever we're going to distill. For example, if we want perfume, roses would be excellent. Yeah.
Rose petals. I'm sure the restaurant won't mind.
I hope not.
And so the water with the rose petals will be heated up here. As the steam's given off, it takes the scent of the roses, it reaches the alembic where it condenses back to a liquid and drips down here into this other container. Who were the people who were carrying out this chemistry?
I think there are 2 main names which stand out above all the others. Above all, Jabir ibn Hayyan, but also Al-Razi.
Jabir ibn Hayyan in particular is very early on in the Golden Age, isn't he? He's regarded by many as the first scientist of the Golden Age.
Yes, yes.
What sorts of things was he doing?
Many of his chemical procedures are those which may still be used today. For example, calcination or precipitation or distillation.
Jabir ibn Hayyan was a polymath who grew up in modern-day Iraq and whose vast work covers medicine, music, alchemy, chemistry, and much more. There are thousands of manuscripts attributed to him, far more than a single man could actually have written. It's believed that many later scholars wrote under his name because he was held in such high regard. Whatever the truth, he's credited with applying an experimental-based approach to early chemistry. The scholars of the Golden Age began applying the scientific method to chemistry, by which I mean they were conducting experiments in a way that was a big leap from the pure philosophical thinking of the ancient Greeks. But to conduct careful experiments, they needed apparatus, much of which hadn't even been invented at the time. And for chemistry in particular, they needed to hone their skills at glass blowing and glass making. And so I'm going to meet a man who's going to show me just how difficult or easy it is to actually carry out that skill. Assalamu alaikum. عايزك تصنع لي آلة كيميائية اسمها الإنبيق اللي كانت تستعمل لتقطير العطور. فإذا أرسم لك صورة ممكن تشوف شكلها. اوكي. انت عندك فكره يعني من اي عصر او قرن بدت صناعه هالالات بالزجاج؟
والله الازاز عموما انا اعرف انه يرجع للفراعنه.
يعني آلاف السنين.
انما التكنيك نفسه بتاع المهنه انا ما اقدرش.
If Jabir ibn Hayyan was making alembics back in the late 8th century, he certainly would have been doing it this way. The sort of glass they would have used over 1,000 years ago would have been very different. They would have put their sand and lead and all the other ingredients into these ovens and just cook them and bake them until they melted. So although they did have glass blowing to shape the molten glass, they didn't have something with such a high temperature like this jet of gas here. Shukran. Wow, that's pretty remarkable. My own alembic. Although Jabir ibn Hayyan and those like him were performing experiments and perfecting apparatus, the work they were doing was very much a mixture of chemistry and alchemy. Indeed, the Arabic word for chemistry is alchemia, from which the word alchemy is derived. But whereas modern chemistry is a rigorous, exact science, alchemy is associated with superstition and magic. The alchemist's main goal was to turn other metals into gold. To his followers, Jabir ibn Hayyan was known as al-Sufi, the mystic, because they believed his work was no different from sorcery. Even today, some chemistry can seem like magic. Afsoon's a chemistry student, and she's going to help me with some demonstrations that I guess could be used as part of a magic show. I'm going to turn these colourless liquids black, simply with the power of my mind. Right, think ink. How about that?
We need to mix these two chemicals together.
Okay.
But first of all, we have to turn off the light.
Here we go. Oh, wow. See, it's not hot, so this is a chemical reaction that's giving off light, but no heat. And for our final trick...
Can you step back?
Yeah.
Thank you.
Of course, for all these reactions, we know that there's a chemical explanation for what's going on. But what we call chemistry has its roots in the alchemy of the Golden Age. So, Peter, To what extent was there real science being done in amongst all this mysticism and alchemy?
You see, Jim, I don't see a contradiction between science and alchemy. Rather, I see a synergy. The one feeds on the other quite often. And that you could say about every period, great period of scientific breakthroughs. You could say it of the Greeks, you could say it of the height of the Latin Middle Ages, you could say it of the Renaissance.
Well, even Isaac Newton was involved in alchemy.
A classic example, yeah.
The early alchemists were obsessed with turning common, less valuable metals into precious gold. Jabir ibn Hayyan in particular was obsessed with trying to dissolve metals, and that led him to research all different kinds of acids. But gold is notoriously difficult to dissolve, so I'm going to buy a small amount of it and see if it's possible. أريد أشتري منك كمية قليلة من الذهب حتى أصنع تجربة.
ممكن نعطيك قطعات زي كده. عندنا ديزاينات زي.
التجربة العلمية اللي لازم أسويها حول حل الذهب في سائل كيميائي. هذا شيء صعب مو؟
شيء صعب انك تسيله في سائل كيميائي، هو عبارة صهره يكون بالنار بدرجات حرارة عالية يعني.
صح.
يعني اما بالنسبة للسائل الكيميائي شيء جديد يعني. وشيء بيكون طيب يعني في هذا المجال اذا كان
في واحد عالم من عمر العصر الخلفاء جابر بن حيان الكيميائي حاول ان يحل الذهب. اوكي اشتريها.
بما انك عميل سوي لك هاي ديسكاونت لانه هاي بنشوف التجربه ان شاء الله.
التجربه العلميه. شكرا جزيلا.
خبرنا احنا على التجربه ان شاء الله مشان نستفيد ان شاء الله منها.
ان شاء الله. Guiding me through my experiment to dissolve gold is Professor Hal Sosabowski. Right then, Hal, I need your chemistry expertise here. I've got this gold coin, and I wonder, is it possible to dissolve gold?
Very, very difficult, Jim. Gold, like all noble metals, is relatively unreactive, but particularly unreactive towards acids. There's only one acid that can really do the job, which is this one, aqua regia, which means kingly water. And it's called kingly water because it's the only thing which dissolves gold.
It's believed that Jabir ibn Hayyan first distilled it, and it's a mixture actually of two acids. It's nitric acid and hydrochloric acid.
Yes, and it's exceptionally corrosive and exceptionally reactive.
It sounds nasty.
It's very, very nasty. It's vicious.
So, can you demonstrate it for me? Let's see if it works.
So we're going to pour it into the beaker. I'm going to save your beautiful gold coin, since you've travelled so far with it, and use this rather more expendable piece of zinc. So off it goes. You can see it's bubbling away. Now, the gold probably wouldn't react as fast as that, but certainly would dissolve away.
And why would people want to do this? Why would they want to dissolve metals like gold?
Because you can purify it, or you can refine your gold by dissolving it and then reprecipitating the metal out.
And although the fumes are still coming up, I think that lump of zinc has been dissolved entirely in the liquid. We did leave a small piece of gold in aqua regia, although this takes a lot longer to react. But over an hour, the gold gradually dissolves.
Neither of those acids on their own will dissolve gold, but taken together they produce the right ions to do exactly that.
But early chemistry wasn't only about alchemy. There was a practical side to it as well. And many developments in chemistry were driven by Islam. Cleanliness was a religious requirement in Islam. For example, the washing of the hands, face and feet before prayer. And this requirement for cleanliness quickly led to the development of whole industries. For example, the development of soap. The first solid bars of soap were found and manufactured in the Islamic world. Jabir ibn Hayyan wrote about the difference between acids and alkalis. And the word alkali derives from the Arabic alkali, which means the ashes of salt wort, referring to the original source of alkali substances. And of course, alkalis are used in soap making. Rima Hazmat runs a small soap-making business in Jordan, where she uses age-old chemical processes to manufacture soap.
Please, can you this the clothes,
Oh, okay.
please? It's very nice.
Thank you.
We put the pure olive oil here.
Okay. Rima makes soap by mixing olive oil with an alkali and then adding her own herbs and spices.
Okay, Mr. Jamil.
This chemical process is called saponification.
And now we're cutting here.
After cooling, the soap is cut into bars and then left to dry for 2 weeks.
This pure olive oil and what?
It's a herb.
Yeah.
Bay leaves.
Yes, this is bay leaves. This is bay leaves. It's good for all the skin and maybe for the hair.
Not for me.
No.
Too late for me. During the Golden Age, soap making was commercialized, and the process started to be developed on an industrial scale. Today, a bar of soap that Rima makes in 2 weeks can be produced in an industrial soap factory in just a few hours. This soap factory is in Leeds in the United Kingdom, and Jamie Bentley is in charge of the plant.
Soap has principally been made in the same way for centuries, a mixture of oil and alkali. We've been making soap here for 150 years, and one of our key ingredients is in this big bulk tank. That's 100 tons of caustic soda, the alkali, to react with the oil.
On this site, they produce about 30 tons of soap per day, around 100,000 tons a year. Industrialized soap making on this grand scale needs chemistry on a grand scale too. And the critical factor is controlling the chemical reaction, mixing carefully measured quantities in temperature-controlled reactors.
So in this reactor, we've got palm kernel oil, which is already in. We're adding the coconut oil, which is the part of the soap that actually creates the foam. After that, we're adding caustic soda.
The mixture is constantly monitored as it reacts, and about an hour later, the reaction is complete. As with Rima's process, once it's reacted, the next stage is to dry the soap.
In here is a vacuum spray dryer. So the soap that's pumped through here, we can create a vacuum and suck the water out of the soap.
Bags of dried soap pellets are sent from the factory all over the world, where they're perfumed and shaped into bars of soap. Soap has been made in basically the same way for centuries, but modern technology, like vacuum spray dryers and precisely controlled reactors, have sped up the process. Modern chemistry relies on being able to weigh and measure accurately. And that's something we can trace back to the Golden Age. One of the reasons we regard the scholars of the Golden Age as the first true scientists is their obsession with accuracy. It's the reason why we think of Jabir ibn Hayyan and Razi as the first true chemists. And here's an example of why. This beautiful set of scales, it was built by a scholar by the name of Al-Khazali in the 12th century. It's called Mizan al-Hikmah, and it's said to be accurate to 1 part in 60,000. If you look very carefully along the arm, you can see very precise graduations giving us the distance from the center. And as the cups are hanging from different lengths, it's basically the principle of moments. As they move out, they will pull it down. The balance is achieved when the diamond shape in the middle is exactly vertical. It's very, very precise. But apart from that, it's actually a beautiful work of art as well. Accurate weighing and measurement allowed early chemists like Jabir ibn Hayyan to be more rigorous in their experiments and their approach to all aspects of chemistry. And this included the way he looked at materials, grouping and categorizing them. Categorizing substances enables us to navigate our way around the scientific world. Just like in this bazaar. Over here, I'd find carpets. Over here, lights. And after the lights, textiles. And over here, ceramics. What Jabir ibn Hayyan did that was different was categorize substances not according to arbitrary factors, but according to the way they behaved in experiments. This was a huge change on what had come before. Back in the lab, I wanted to find out what Hal, as a modern chemist, thought of Jabir's early attempts at categorizing. And I wanted to show you this extract from a manuscript of his. So this is translated from Arabic into Latin into English. It says here, among all bodies of whatsoever kind, we find Sol, which is gold, not to be burned by sulfur. So it's the least reactive with sulfur. Sure. The next to this least burned is Jupiter, which is tin, then Luna, which is silver, and he goes on. And so he ends with, and Mars, which is iron, by reason of the oleaginy of sulfur, is most easily burned. It's all very obscure. In fact, the word gibberish actually comes from Jabir's name. If you write something too obscurely, it's gibberish. Sure. It's like Jabir. But what he has here seems to me the beginnings of the reactivity series for metals, listing them in order of how easily they react with sulfur.
Yes.
How correct was this?
Well, there was a couple of little inaccuracies in it, but he was way ahead of his time because showing reactivities with sulfur is often quite difficult. So what I thought we'd do is we're going to compare and contrast the reactivities of certain metals with water. Iron, for example, which he mentions, we all know that iron rusts. So that's a slow reaction, but we're going to compare and contrast a triumvirate of metals and see how fast they react. And they are potassium, sodium, and copper. I thought we'd start with the most reactive. This is potassium, and it's very soft and malleable, and you can easily cut it with a knife. So 3, 2, 1, in it goes. And off it goes.
Oh,
a lovely
very impressive.
lilac flame that's being formed, and it's popping around because it's producing hydrogen.
Oh.
And we're going to move on to our next metal, sodium. Sodium chloride is common salt, but sodium has got very, very different properties. It's, again, a metal you can cut with a knife. 3, 2, 1, and it goes. And it's buzzing around. And,
oh, isn't that pretty?
It's probably going to melt because of the heat of the reaction. Just
you can hear it.
It's hissing away, yeah? It sounds like a wasp in a bottle.
So it's lasting longer in the water. It's not reacting so quickly.
And by way of comparison, just to eliminate all the variables, this is copper.
And we don't need that.
No, we don't need this because the copper will do absolutely nothing. It's very unreactive, and that's why the coins in your pocket don't catch fire if you put them in the washing machine.
The washing machine, get them wet. And so this order of just how reactive metals are, I mean, by modern standards of chemistry, Jabir ibn Hayyan didn't get it quite right. He had metals in the wrong order in that series. But how impressive was that, given that we're talking, you know, over 1,000 years ago?
It's exceptionally impressive because he just didn't know what he was looking for. He didn't know what to expect. We know these things because we look at the periodic table.
So you would call that chemistry, not alchemy?
I think it's definitely chemistry.
Jabir ibn Hayyan was starting to apply the scientific method, deriving his conclusions from experiments. And later chemists like Al-Kindi and Razi were also basing their work on careful experiments and observations. And the way we do chemistry today, organizing and ordering the elements and looking for trends in their properties, well, just like the reactivity series, that's what Jabir first started to do. Next time, we travel to some of the most cutting-edge medical facilities in the Middle East today.
The original human genome was sequenced in 10 years. Now we can sequence the human genome within 6 to 10 days.
We look back at how one scholar from the Golden Age challenged accepted ideas to explain the human heart.
This is the pulmonary circulation. That is the discovery. It's now obvious, but it wasn't then.
and see how texts from the Islamic world were so influential in medical science across the globe for centuries.
Science tends to be a good subject to bring different people from all over the world together.